Hello, my name is Ushnish Sengupta and I will be presenting our Turbo Expo paper, Bayesian Machine Learning for the Prognosis of Thermoacoustic Instabilities from Noise. I'm doing my PhD in the University of Cambridge's Department of Engineering, where I'm supervised by Professors Carl Rasmussen and Matthew Juniper, who are also my co-authors on this paper. A flame in an enclosed space naturally has perturbations in its heat release rate which make it radiate acoustic waves. These waves may be reflected back onto the flame by the combustor walls, producing further heat release rate oscillations, which in turn produce more acoustic waves. Depending on their relative phase, the heat release rate fluctuations and acoustic oscillations can potentially feed more and more energy into each other, leading to large amplitude vibrations known as thermoacoustic instabilities. In this video, we saw a tube being lowered onto a Bunsen flame in our lab and the fundamental acoustic mode of the tube being excited as a result. While this is but a mild annoyance for the unfortunate people near our lab, in high energy density combustors such as those we find in rocket engines, gas turbines, or aircraft engines, these instabilities can have devastating consequences. Damage can result either directly from pressure oscillations or the enhanced heat transfer rates which sometimes accompany these instabilities. So, as engineers, what tools do we have at our disposal to fix these instabilities if they do crop up? The first and best wall of defense is of course a good design. If we have an accurate model of our system, we can then use it to tweak the design, let's say by adding dampers or by changing the geometry, and stabilize the combustor thus. However, despite our best efforts at the design stage, this may not always be possible because thermoacoustic instabilities are highly sensitive to system parameters, so our models may be inaccurate, or the required tweaks may come into conflict with other more pressing design objectives. We then retreat to our second wall, avoiding unstable regions in the operating parameter space. This means that we operate the engine such that we avoid conditions under which thermoacoustic instabilities are known to be triggered. If even this proves impossible and we are forced to operate the engine under conditions which are known to be unstable, we retreat to the final wall, active control. This involves adding just the right kind of external pressure oscillations, using secondary controllable acoustic sources to exactly counteract any budding thermoacoustic instability with destructive interference. In this study, however, we are primarily concerned with the second wall of defense, that is, avoiding instabilities during operation. Specifically, we will be looking at how information hidden in the noise radiated by a turbulent combustor can help us deftly dodge any potential instabilities. This paper was partly inspired by a 1966 article by Mark Keck in the American Mathematical Monthly. Can one hear the shape of a drum? Here, he asks if one can determine the shape of a vibrating membrane, given only the list of its eigenfrequencies. Later, Zeldich proved the surprising result that it is indeed possible to determine the shape of a vibrating membrane from its spectrum if the membrane boundary is planar, convex, and analytic. If the vibration spectrum of a membrane can encode so much information, it makes us wonder what we might learn about the state of a turbulent combustor from the power spectrum of the noise that it radiates. Let me play a little clip for you. Did you catch that? That was a 300 millisecond sample of noise from a turbulent combustor. While not exactly Beethoven, it might nevertheless have a lot to tell us. Can the spectrum of this little bit of noise tell us how close we are to a thermoacoustic instability? What other information can we recover from it? To investigate these questions experimentally, we built a little setup in our lab. It is a small, pre-mixed, turbulent swirling flame inside a steel tube that can burn a few kilowatts of fuel. The fundamental mode of this tube is observed to become thermoacoustically unstable at high powers and high equivalence ratios. Our fuel is a mixture of methane and ethene, and the flow rate of methane, ethene, and air can be controlled by mass flow rate controllers. At one end of the tube, we can fit annular plates of different diameters to vary the boundary condition, and at the other end, we have a microphone that records pressure data as well as a loudspeaker, which we use to excite the combustor with short acoustic pulses. The decay rates of the pulses allow us to quantify the linear stability of the combustor. To show you what I mean, let me play another clip. Okay, so what you just heard was the combustor happily buzzing away, making its combustor noises, and then we excited it with a short acoustic pulse from that loudspeaker, which slowly died off. The closer to instability our combustor is, the longer it takes for the pulse to decay, and we can use the rate of this exponential decay as a measure of how stable the combustor is at a given instant. The system is operated at 900 different combinations of operating parameters, which form a grid in our four-dimensional operating parameter space. The four dimensions being the volumetric flow rate, the equivalence ratio, the methane to ethene ratio, and the outlet boundary condition. This wide range of configurations included very thermoacoustically stable operating points as well as points which were right at the edge of instability. Experiments were performed at methane to ethene ratios of 3:4, 1:1, and 5:4, and tube outlet diameters of 80, 75, and 65 mm. For each of the three methane to ethene ratios and each of the three outlet boundary conditions, we methodically swept through 100 different fuel and air mass flow rates. The figures on this slide show the 100 pairs of equivalence ratios and volumetric flow rates at which experiments were performed, while the methane to ethene ratio and outlet diameters were fixed at 0.75 and 80 mm respectively. At each operating point, we recorded samples of the combustion noise and measured the decay rate of an acoustic pulse at the fundamental frequency, as described in the previous slide. Armed with this large dataset, we then set ourselves the following challenge. Given the power spectrum of a 300 millisecond sample of combustion noise, can we estimate the decay timescale, that is the inverse of the measured decay rate at that operating point? If it were possible to do this, that would mean that we can use the spectrum of the noise to warn us when the combustor is nearing an instability. Also, to verify our hypothesis that the spectrum of the noise might be a fingerprint of its state, we also wanted to check if it was possible to recover the burner power and equivalence ratio of the flame when a noise sample was produced. These are essentially all multidimensional regression problems with a large dataset, and therefore an ideal use case for machine learning. Our machine learning tool of choice is the Bayesian neural network, and we will justify this choice in the slides that follow. So what is this Bayesian machine learning and how is it different from traditional machine learning techniques? Machine learning essentially involves learning some functional relationship between inputs and outputs. The typical machine learning algorithm will usually give us a point prediction, but this might result in overconfident and wrong predictions, particularly when one is given inputs that are very different from what was seen during training. This is undesirable in high-stakes use cases, like an aircraft engine. Bayesian machine learning circumvents this problem by working with distributions over functions instead of point estimates. Before observing any data, a Bayesian algorithm only has a vague prior probability distribution over possible functional relationships between the input and the output, and has large uncertainties in its predictions, regardless of input. As more data points are observed, the algorithm uses Bayes' rule to figure out the posterior distribution, becoming more confident near observed data points, but still retaining uncertainty in regions where it lacks data. This has been depicted in the two images that are on this slide. How does one define and manipulate distributions over functions in practice? Let us try to understand this with the example of Bayesian linear regression, where we assume that it is known that the relationship between inputs and outputs is linear. For simplicity, Let us assume that we have one input variable x and one output variable y, related to each other by the simple equation y equals w1x plus w0, where w1 and w0 are unknown parameters. In the top row, where we haven't yet observed any data, we can only assume a vague prior probability distribution for w0 and w1. On the right-hand column, you can see that samples taken from this vague prior suggest all sorts of different linear relationships between x and y which might exist. And this is sensible, since we do not yet have much of an idea about how x and y may be related. On to the second row, where we have now observed one data point. Using Bayes' rule, we can derive the posterior distribution over W0 and W1, which is tighter than the prior that we had before, but still pretty diffuse. From the generated samples on the right, we see that we are still generating lines that are all over the place, but at least now most of them are passing pretty close to that one observed data point that we have. On to the third row, where we now have two data points, and this time the posterior over parameters becomes much tighter. And on the right-hand side, we see that while there is still uncertainty, we now have a rough idea of what the linear relationship between x and y is supposed to look like. In the fourth and final row, we now have many data points, so the posterior has collapsed almost to a single point, and on the right-hand side, we now have much smaller uncertainties in y. Of course, in general, we expect our inputs and outputs to be related nonlinearly. One way to specify distributions over nonlinear functions is a Bayesian neural network. A neural network, as some of you might know, is a nonlinear compositional map between an input vector and an output vector that is typically parameterized by a large number of parameters. Just like the linear case that we saw in the previous slide, we can start with vague prior distributions over all of these parameters and then use observed data points to arrive at a posterior. Unlike the linear case, however, there is no closed form solution, since the posterior is no longer a simple Gaussian. This is why we are forced to use approximate inference techniques. In this paper, we use a state-of-the-art inference technique known as randomized map sampling proposed by Tim Pierce and co-workers in Cambridge, which is computationally cheap and fairly accurate. This algorithm involves training an ensemble of neural networks, each of whose parameters is initialized with a different random sample from the prior. They are then trained using a special loss function which not only tries to minimize mean squared error, but also tries to anchor the parameters of the neural network to that sample that was taken from the prior. After training, each trained ensemble member may be treated as a sample from the approximate posterior. So the variance of the different predictions made by the ensemble members give us our desired uncertainty. So we assign noise samples from 80% of our 900 operating conditions to the training set and 20% to a test set. The power spectra of the noise samples is obtained simply by using the fast Fourier transform, and these are then directly provided as inputs to our Bayesian neural network ensembles. Hyperparameter tuning was performed, and a simple two-layer neural network with 25 units was found to work quite well. We find that the trained neural networks can indeed successfully predict the decay timescale from the noise spectra. In this figure, we show the performance of the neural network on the unseen test dataset by plotting the real measured decay timescale corresponding to a noise sample versus the one that was predicted by the neural network. In an ideal world, all the red points would lie exactly on the dotted x equals y line. But of course, the noise is not a perfect source of information, and we do have some error in our predictions. We also find that the estimates of uncertainty provided by the Bayesian neural networks are very reasonable. We also find that the network is able to accurately predict the equivalence ratio and power of the flames which produced a particular noise sample, confirming our hypothesis that the noise is a fingerprint of the combustor state. Clearly, each operating point has a distinct noise spectrum, and this one-to-one correspondence has been learned by the Bayesian neural network. Unlike simple linear models, neural networks are notorious for being hard to interpret, which is not ideal if you are deploying it in high-risk settings. For deep neural networks, the gradients of the output with respect to the input is a natural analog of linear regression coefficients. The difference is that in the linear model, the coefficients characterize the relationship between the input and output variables globally. But in a nonlinear neural network, the gradient at a point merely characterizes the local relationship between the predictor variable and the output. The main idea behind the interpretation technique that we use here, known as integrated gradients, is to compute the path integral of the gradient of outputs with respect to input variables from a baseline input to the input at hand. For an image recognition algorithm, a completely black image could be a reasonable choice of baseline, while for a regression problem like we have here, where the input variables were normalized to lie between -1 and 1, an input of all zeros is a reasonable choice of baseline. We consider the straight line path from the baseline x' to the input x and numerically compute the line integral of gradients of the output with respect to the ith input variables along this path to obtain the attribution corresponding to the ith input variable. Accumulating the gradients with the path integral ensures that we estimate the aggregate influence of each predictor instead of just the local influence. Here, we show integrated gradients being applied to an image recognition neural network, where we try to estimate the influence of each pixel on the final prediction of the neural network, the prediction being that this is the image of a garter snake. On the right-hand side, the deep blue pixels are the ones that, according to integrated gradients, are making the neural network think that this is a garter snake. As human beings, we would surely agree that those are the snakiest pixels, which means that the tool is working. This figure shows the integrated gradients attribution obtained for a noise sample corresponding to an operating point that is quite near instability. What's noticeable here is that although there are some dominant contributions, particularly the positive contributions from the fundamental and the third overtone, every frequency component in the power spectrum has a significant contribution to the final prediction. We are naturally not the first to use noise as a diagnostic instrument, particularly for thermoacoustic instabilities in combustors. The novelty in our paper is that we use data-driven measures that use information from the entire noise spectrum instead of filtering the noise data through handcrafted measures, which is the approach that has been taken in previous studies. Here we compare with two well-known early warning measures of thermoacoustic instability from the literature, namely the Hertz exponent, which was proposed in a paper by Nair and colleagues, and the autocorrelation decay, which was proposed by Tim Lewin. We find that these measures generally behave as expected. The Hertz exponent decreases as the combustor nears an instability, while the autocorrelation decay becomes close to zero. However, this relationship is fairly noisy, which might make them unreliable as early warning measures. However, the physically inspired measures from the literature have the advantage that they do not need to be trained on extensive experimental databases. In conclusion, we found that the spectrum of the noise radiated by a combustor is a rich source of information about what's going on inside it. We used Bayesian machine learning to recover from tiny 300 millisecond samples of combustion noise both the equivalence ratio and power of the flames that produce them, as well as the decay timescale, which is a measure of how stable the combustor was when it generated that tiny snippet of noise. The Bayesian model also knows what it doesn't know and provides measures of uncertainty with every prediction that it makes. It is not a complete black box either, and we used integrated gradients to gain insight into what it is in our power spectra that the algorithm finds useful for making predictions. Compared to physically inspired early warning measures from the literature such as the autocorrelation decay or the Hertz exponent, we find that the machine learning techniques were more reliable indicators of closeness to thermoacoustic instability. We are testing the algorithms that we developed in the lab out in the real world as well. Our collaborators in the German Aerospace Center in Lampushausen operate a 90 megawatt rocket engine combustor they call BKD, which also exhibits thermoacoustic instabilities. We find that when these tools are applied to data from this combustor, we are able to forecast thermoacoustic instabilities better using the noise recorded within the combustor. I hope you found this overview of our work interesting, and if you want to find out more about what we did, please read our paper or check out our GitHub repository, which has the data as well as the code that was used to produce these results. Thank you very much for your attention.